Let's see. Here a little early just to kind of give everybody some time to get in. Try to put this up a little bit. See if the sound is okay. See, yoink. 8:29. If I have any students listening right now, maybe you don't mind confirming that the sound is okay in the chat before I get babbling. So let's see. Try this. Sound okay? Thank you, Braden. All right, you guys. Let's do a quick little review. This is so weird because again, it's like driving a boat. Okay, see if I get this in here. So I drew a Cartesian plane for us to associate with, and I want to remind you that resultants are like obviously they're vectors I have right there, and unless you apply that resultant either here, here, there, or there, remember only 4 places and 360 degrees of options, there's going to be some combination of x and y component in that resultant. The resultant is just basically what you measure. It's your overall velocity, it's your overall displacement, it's your overall acceleration, it's like your so what, the overall force. But outside of applying those different vectors quantities in exactly positive x, exactly negative x, positive y, there's going to be some component of x and y. Okay, so I reminded you about, or I talked about the angles. Like in anatomical, we had global and local references. For angles, it's the same thing. In quadrant 1, our relative and absolute angle are going to be the same, kind of like in anatomical, local and global can be the same. But once we drift off into 2, 3, and 4, our absolute angle, our global angle, is going to tell us where that resultant is being applied. So 100 degrees from the horizon, 100 degrees isn't a right triangle, but I know that to get to 100, I have to pass 90. So once I drift over 10 degrees from 90, I know that I'm 10 degrees into quadrant 2. That makes sense? So our overall angle, like our absolute angle, would be 100 degrees for communication reasons, but our relative or local reference would be from one of these kind of landmarks, right? I'm 10 degrees into quadrant 2. Then we talked about a little shortcut. Now, I'm trying to feel like I'm in the circus trying to juggle this stuff. But if we go back to our calculators, okay, we need to take the scroll off so that we can see it in here. I mentioned that where you are in the quadrant is going to prove or show you which component you're measuring with sine and cosine. So in other words, don't overthink sine and cosine. They had to name it something, but these sine and cosine functions are just means of getting how much of that resultant in terms of a percent is at a given angle. That's all it is. So in other words, if all of our resultant was in the positive x, it would be 100% of that resultant. Right? So like so at 45, we talked about like it's going to be equal, right? And then as you get past 45, there's going to be more y than x. As you get shallower from 45, more x than y. That was last class, okay? So let's complete our our little practice that I gave you. So we're going to do the shortcut because shortcuts work, and shortcuts, I think, make more sense than long cuts. Okay. So watch quadrant 1. I'm going to do 20 sine 34% of my resultant is going to be, think of it like this. 34% is smaller, right? It's a small percent. So my sine function of that angle at 20 degrees, the sine, the opposite, that's going to be my y component. That makes sense. Well, the y is going to be kind of small. Versus if I did 80 sine for my y component, 98%. Now, again, I want to show you the magic. 20%, or I'm sorry, 20 degrees from the horizon, 34% of that component is y with that resultant. If I drift off to 80 degrees from the horizon, that jumps all the way up to 98% of that resultant is y component. Okay. Drift off into quadrant 2, 100 sine, once again, 98%. So what we just did is we said, okay, if I'm at 80, I'm 10 degrees from 90. 98% of whatever my resultant is going to be y. It's going to be up. And if I drift 10 degrees past, still 98 degrees is going to be up. Because remember, both of them would be in positive y. The x would be negative, but the y would both be positive. And the reason I'm emphasizing the percentage is because when you need to find out, well, 98% of what? Well, that's why you cross multiply with your result. 98% of 50 miles an hour, 98% of 100 miles, 98% of 200 pounds. That's why you cross multiply. So you find the percentage, how much of a percentage is that component x or y, and then you just multiply by what the resultant is. And that gives you how much of that is x or how much of that is y. Okay. All right, quadrant 2 were velocities. So we just did 100. Let's do 135. We'll go 135 sine. 70% of that is going to be y. Okay. 135 cosine. 70% of it is going to be x. That makes sense. 135 is halfway into quadrant 2, right? Absolute 135, but relative, it's 45 degrees past 90. It's the same place, right? So both the x and y components will be 70% of the resultant. Like driving a boat, okay? Now, 70% of what? Well, in quadrant 2 examples, I gave you a velocity. So 70% of 50 miles an hour. So then you would just multiply by 50, and then it would give you the actual velocity, like 35 miles an hour in the negative x, 35 miles an hour in the positive y. Okay. Make sense? Okay. Let's do quadrant 2, that last one, 170 degrees sine small. That makes sense. 170 is very shallow, so the y velocity isn't going to be a high percentage of the resultant. Here, only 17%. But if I wanted to look at the x, that should be a large percent. So let's do 170 cosine at 98%. And notice that negative, it doesn't mean I owe you a percentage. It just means that it's in that direction. That's what that tells you. Okay. Direction matters with vectors, right? Okay. So I think you get the gist. All right. Now, what I'm going to talk about now, or segue to, is forces, because the last 2 quadrants are forces, and there's a little something we got to talk about before we go into forces. Sense of a vector. So like if if I measure something and it has a velocity of 50 miles an hour, right? The X and Y component will be in miles an hour. It'll be the same sense. It's moving in the X, it's moving in the Y. If I have a displacement, the X and the Y component will be the same sense. It's this many miles X, this many miles Y. But when we get to forces, it's a little hinky, as my major professor used to say. She was from New York, so they have a little different vocabulary. It's a little weird. With forces, some of the forces, especially the kind that we use in activities of daily living and biomechanics, sport, performance, the resultant force can have two different senses. It can have two different types of force. And I'm going to use push or compression for all of these examples because that's really what I'm talking about. When you push onto something, right, and you're compressing those two surfaces together, be mindful that you're interlocking. See how my knuckles are interlocking? You're compressing those two surfaces that are always going to be imperfect. They're always going to have, I always think of Ruffles potato chips because they have ridges. Ruffles have ridges. And when you compress two surfaces, even though it may seem smooth, you're compressing imperfect surfaces together. Okay. So these two surfaces are trying to influence each other's motion through a direct linear push. But what if you get to, this analogy may work, it may not work, but what if you get like to a T in the road where you can't go any further? So like you're compressing these two surfaces together and they're not going to push past each other. That would be like Harry Potter magic. What are your options? Well, one, you can uncompress them, but there is a second option where the two objects that are compressed together could potentially try to move or apply influence perpendicular to the push. Okay. And that is a specific type of force that we call friction forces. And I like to oversimplify everything. So friction forces to me is like microscopic push. Like it's the little pushes of my knuckles on each other this way because I have my fist pushing this way. But it's the actual interlocking of the knuckles that are kind of pushing perpendicular to the compression. And that's what friction is. Friction's weird because we use it so much, so often. Walking around, it's friction. Think about injuries. I slipped or this slipped out of my hand, or a quarterback, the ball slips out of the hand or anytime you have slippage, that was a failure of friction forces to kind of do their job. Mardi Gras is here, man. We're going to be a lot of crawfish is going to be cooked in the next few weeks. So imagine grabbing a sack of crawfish. You're going to compress your hand, right? You're going to grip around the sack, but you're not going to lift that sack up unless there's sufficient friction that's perpendicular to the compression. In fact, if it's slipping out of your hand, if anything's slipping out of your hand, what are you going to do? You're going to squeeze it more. You're going to increase the compression. Okay. And so friction is kind of that hidden force that's there that's so important in all of our everyday lives. And the reason I want to introduce with that is because when we have a resultant force, okay, so let's say for this example that I'm going to give you on our sheet, force of 100 pounds applied to an angle of well, the quadrant 3, let's do the third question in quadrant 3. A force of 75 pounds is applied at an angle of 260 degrees from the horizon. Okay. So that would be, let me try to draw it as best as I can. So yoink. Okay. So that would be like around here, because 270 would be negative y. So right away, I know some things about this resultant. One is I can't draw very straight. That's the first thing I know. Two, the y component of that force is going to be negative y, down. And the x component of that force is going to be negative x, or across, right? Now, for forces like a push on the ground, imagine if we've done this in class, but imagine like you're pushing off of the ground, like to jump or to run or to walk. Okay. So if you're walking this way and you're like towing off on the ground, this is the force, or the force that you would be pushing on the ground. You'd be trying to push the ground down, but lucky for us, the ground usually doesn't go anywhere unless we're on the beach. And you're also trying to push the ground back. Remember, you're walking this way. This resultant is one force. Like if I had a scale of what we call the force plates, right? This is what it would record. But the x and the y component of this resultant have two different force senses. One is a direct compression. That's why we call it a normal force. It's the component of a resultant force that's literally directly pushing, macro push. And then perpendicular to that, in this example, is the micro push, the friction. Friction is still a force. So it's part of this, but it's not exactly the same kind of force as the normal force or the direct compression. Their sense is a little different. They're concurrent because they're happening at the same point, but they're not the exact same type of force. To me, the best way to summarize kind of how different these forces are, they're similar, but they're very different, is if you're going to create friction on your hands like we used to do, we still do, right? And one of the byproducts of that is heat. But if you were going to create friction in your hands, those hands have to be compressed. You have to have direct compression in order to interlock those two surfaces to have the potential to have micro compression. If your hands are not interlocked, you will not have friction. Those surfaces have to be interlocked. They have to be compressed. And the more you compress them, the more potential you have for friction forces. Make sense? In addition, usually imperfections is like thought of as a bad thing, but it's actually a very good thing. We want to have imperfect surfaces when we grab and grip and hold. That's why we have fingerprints. Our fingerprints, if you think of it, are imperfect ridges and grooves that we can use to interlock with other imperfect, even if it's smooth, there's imperfect surfaces in there. So our fingerprints are there so that we can compress surfaces, create interlock, and then be able to create friction forces that are perpendicular to that compression in whatever we're trying to do. Sport, skill, activities of daily living. You think about shoes, like the bottoms of shoes, they're not smooth, right? They're imperfect on purpose to try to grip. In fact, when when you're playing ball and the court is all dusty and dirty, that's why you slip around, because in those imperfections, you get dirt and grime and stuff that fill in these imperfect surfaces. The surfaces become smooth. So what do? You try to clean it off, get it out of there, because you want imperfect surfaces to interlock. Okay. One of the reasons I just think this is cool, but when you're underwater for a long time and you get the prune hands, that's your body's way of trying to re-emphasize imperfect surfaces to interlock in wet conditions, knowing that you're going to have water get into the surfaces to try to mess with your interlock. So it re-emphasize those imperfect surfaces. You make them pruny so that you could really try to grip and hold if you're working underwater and water for a long time. Okay. So when we're talking about forces in class, they're usually going to be down. Usually when we're talking about like the ground forces and stuff, it's going to be down. But that doesn't mean all forces, frictions have to be down. Leaning up against a wall, right? I can lean up against the wall, and now it's like my hand is my foot, and I'm compressing, and I can have friction perpendicular to the compression. So not all friction has to be X, just like not all compression has to be Y. Okay. So I have a couple examples here that I wanted to show you before we finish the rest of the examples for class, but I drew some little squiggly lines, some little squigglies. So if you think about if I wanted to erase these squigglies, direct compression, like if I push into the board alone, isn't going to erase that squiggly. Direct push isn't going to erase that squiggly. But I have to have direct push to give the environment for the friction forces that are needed to erase that squiggly. That makes sense. So in other words, I gotta compress, and this would be into the Z. Let's see if I can make it work like we've been practicing. I'm gonna compress into the X, and then my friction is gonna be in the Y. That makes sense? So I'm gonna compress, and then friction forces, and then you erase it. So the friction forces. Now, where it does get confusing is the friction forces are in the Y, but who's feeling what? Remember with Newton's third law. So I have the eraser feels the dry erase board, and the board feels the eraser. In this example, the board would feel the compression this way from the eraser, right? Board feels this. So the eraser has to feel that. So board would feel a negative X push. The eraser would have to feel a positive X push. So far, so bad. Now, when we get into friction, that gets a little confusing of who feels what, because it's just not traditional. We don't think of it as much as we do the direct compression stuff, okay? So I'm going to try to help you see it. We're going to use ups and downs. Compression. If I move the eraser up, I'm pushing or shifting the dry erase actual ink. Aren't I like smearing it up? I wish it would actually smear. When do you smear when you want it to smear? Like I'd be pushing it up, right? Like if it was to smear. So when I take the eraser and I shift it up, that's friction of what the board and all of the markers feel. The board would feel positive Y friction from the eraser when I would do this. And when I come down, wouldn't I be trying to drag the ink down? So the board and the ink would feel negative Y friction from my eraser when I would be doing down. So positive Y friction felt by the board, negative Y friction felt by the board. Positive friction, negative friction. Positive Y, negative Y, positive Y, negative Y. positive y, negative y, positive y, negative y, positive y, negative y. Now that's what the board feels. Newton's third law says, well, if the board is feeling positive y friction from the eraser has to feel negative y friction from the board. So that's where things get confusing. It's just who's feeling what, who feels what. And that would be like, this is black ink, but let's just say I dipped this eraser in like red ink and I compressed it and I did positive Y friction on the board. Well, I would leave a trail of red ink going up because the board is dragging that red ink down because the eraser feels negative drag, negative friction from the board. Remember, they have to feel each other's influence in the same sense. Friction for friction, push for push, compression for compression. So board feels a backward force. I'm not going to rotate. I'm going to keep it like this. Board feels a backward force from the eraser. Eraser has to feel a forward force, push from the board. Board feels positive friction from the eraser. Eraser feels negative friction from the board. Board feels negative Y friction from the eraser. Eraser feels positive Y friction from the board. Okay. And then I did this one because, again, friction doesn't have to just be up and down. It could be across. So I have these little squigglies to kind of show that. Okay. There's some compression with no perpendicular micro push. Doesn't erase. So what I'm going to do is I'm going to compress, and look, if I don't compress, I won't have friction. Right, left, right, left, positive X, negative X, positive X, negative X, positive X, negative X. So in this example, as I go positive X, the board is going to feel positive X friction from my eraser. Therefore, the eraser has to feel negative X friction from the board. As I go back, the board's going to feel negative X friction from my eraser. Then the board's going to feel positive X. Then the board's going to feel negative X. Then the board's going to feel positive X. Then the board's going to feel negative X. Okay. So what are, for friction, two factors? What are the two surfaces made of? Because to have friction between things, there has to be things. You have to have two different things interacting with each other to have friction forces. Some of you in physics may have heard this fancy term. Dr. Madsen didn't like it very much. Coefficient of friction. The co is two things. What are they made of and how much are they compressed together? But Madsen was always very adamant about the coefficient of friction is just one instantaneous measurable moment. Friction is going to constantly be changing. Even static friction, those numbers are always changing. So he just liked to use a kind of a more layman's term, friction forces. Okay. So let's get back to our quadrant 3 examples with force. And these are specifically pushes that are going to be into other objects. So like, so look at the quadrant 3, a force of 100 pounds applied at an angle 190 degrees from the horizon. That would be like if I was leaning up against a wall. Okay. So let me apply a little friction to this right here. Force of 100 pounds applied at an angle 190 from the horizon. Let's find it. 90, not there yet. 180, almost there, but not there yet. I just have to go 10 more degrees, bang. There I am. So a force of 100 pounds applied at that angle up against the wall, right? So I'm leaning against the wall, but my arm is not perfectly vertical. I'm not applying that push directly in the positive X. I'm a little below it. So that tells me that some of that resultant force, that tells me some of that 100 pounds has to have a little bit of friction to it. Make sense? So trigonometry is going to help us say how much of that 100 pounds is direct compression, normal force, and how much of that 100 pounds is friction, micro compression, micro push. Think of it like this: that friction is going to prevent me from sliding, right? So having it there, super useful. So let's take out our our little calculators, and let's do the Y component. Now we know that the Y component, if I'm leaning up against the wall, is going to be our friction, okay? Because our compression in this case is our X, right? So I'm going to go 190 sine negative 17%, 0.17. Yoink. So again, what does that mean? That means that of that 100 pounds, 17% of it is going to be here, which makes sense. I'm in quadrant 3. Quadrant 3, the X component is going to be negative and the Y component is going to be negative, okay? Yeah, absolutely. Let me I'm going to finish with this one, and then we'll do 10 sine. Not a problem, Olivia. So how much of that 100 pounds is friction? Well, I know the percentage of the 100 pounds. So all I got to do is just multiply 17% times 100 and yoink. Let's see. I pressed a wrong button, so I got to start all over again. Okay. So I'm at 190 sine times 100. Oh yeah, the 100 is gonna move the decimal place. So 17 pounds of that 100 pounds is being applied down to the wall. Think of it like this: I'm trying to chip paint off the wall with 17 pounds of force down, if that makes sense. Okay, so I'm leaning up against the wall, but I'm not exactly at 180. I'm a little down. So of that resultant force into the wall, 17 pounds is trying to shift paint off the wall in the downward direction, okay? Well, how much of that 100% is directly compressed into the wall? So what I'm going to do is I'm going to go 190 cosine. That's a big chunk, 98% of that. So I'm going to multiply that by 100 and bang, 98.48 pounds of that 100 pounds is trying to push the wall that way, right? I'm trying to break through the wall. So there's my X, there's my Y. It's a little small y, it's a big X, and the combination of those two gives me my resultant at 190 from the horizon, okay? All right, Olivia, so let's do, where's the 10 sine? Was this an example, or you just want to do, or do you want me to just explain it 10 degrees from 180? Because I could do that too. So quadrant 3, a force of 10 pounds applied at an angle of 190. So instead of what you would do is, if you wanted to do it relative or local, you wouldn't do 190 sine. All you would do is just say 10 sine, and you see how you get the same thing. The only thing is you would get the same magnitude, but you wouldn't get the same direction, because if you just type in 10, your calculator thinks you're in quadrant 1 because everything's from the horizon. So if you just did 10, your calculator is but that's not a deal breaker. You just know that that component is negative because 190 showed you that you're in quadrant 3. So you could still do 10 sine, but you have to put in the direction. You have to remember that, oh, that 17% of that resultant is in the negative one. So if you do it global on your calculator, it'll do the direction for you. But if you keep it local, then you just have to remember to apply that direction in there. I hope that answered your question. If it didn't, follow up with it. Okay, let's apply a 75-pound force at an angle of 225. You're very welcome. Now, this could be a couple of things. We could apply this 75-pound force to the wall where I wouldn't be as across. I would kind of be halfway, right? I'd be halfway down. Or we could apply it to the ground, like if you were doing like a vertical jump, or I'm sorry, a standing broad jump. You would have much more of a combination of force from the ground. But note that your friction is dependent on your compression. Like I said it earlier, you can't have friction without compression. You can't have friction forces without normal forces. You can have normal forces without friction forces. So in other words, just because two things are being compressed together doesn't mean they're trying to move perpendicular to them. So you can compress without having friction, but you can't have friction without compression. Okay. All right. Quadrant 3, force of 75 pounds is applied. Just for this example, let's do the wall because the wall's like right there. So I'm leaning up against the wall, but instead of like leaning like here, I'm kind of like down here. Okay. So it should kind of make some logical sense that I'm trying to chip more paint from the wall, right? I'm going to have much more of a friction component of my resultant. Okay. So let's see what that comes up with. I'm just going to do the calculations here with you guys. So 225 sine is going to give me my y component. That's 70%. We've done this one before, the midway, right? It's also going to tell me my direction, make sure I don't mess with that direction, times 75, 53 of that 75 pounds is negative y friction. And then 53 of that 75 is going to be negative x compression. And remember, 75, our instinct wants to say, well, if you're halfway, x and y is going to be the same. True. But that doesn't mean they're going to be exactly half of 75. That was from Wednesday's lecture, right? So it should make sense that A plus B is greater than C, because for trig to work, we got to square it all. So 53x and 53y has to be greater than the 75 resultant. Okay, that's okay. All right, 75 pounds. This is example 3 in quadrant 3. 75 pounds applied at an angle of 260. Well, that's going to be very steep. I know that my y component has to be greater than my x component, right? So I'm going to go 260 sine, huge percentage. That works out. So I'm going to cross multiply that by 75 pounds. Go 70, almost 74 pounds of that 75 pounds is y. Now, I'm not going to, that doesn't make a lot of sense for the wall because I can't, remember, I have to have compression, I have friction. So there's a limiting factor to, you have to have more compression than the friction. So this example would be much more realistic to the ground, pushing on your ground. Like if you were going to do a vertical jump, let's say, this would be a great example for a vertical jump. 75 pounds of force applied at an angle almost perfectly straight down, but not quite. You're a little bit here. Now, what's cool, let's not even talk numbers. Let's just have a conversation. You apply a 75-pound force at that angle. Let's just pretend that you're doing a vertical jump and all of your force while you're coming up off of the ground, while you're pushing on the ground, because remember, you're going to get back what you give the ground. Let's say all of that resultant force, that combination of x and y, is at that same angle, 260 from the horizon. That Y component, the direct compression from the ground, is what's going to get you up. It's what's going to get you as high as you can. But you're going to drift a little bit because you didn't put all of your force directly down. So therefore, all the force is coming back up. You gave a little bit of force to the negative X in the form of friction, the form of friction forces. So therefore, the ground is going to give you back a little bit of force in the positive X. And that little bit of force in the positive X, F is equal to ma, the friction that you're going to feel from the ground is going to make you drift a little bit forward. So you're going to land a little bit further away than where you pushed off because of friction. Okay. So friction is one of those things that we know of, we talk about a lot, we use in everyday lives, we play fast and loose with. But for our class, when you start to work into your individual projects, your skill projects, friction is going to be very important for basketball, right? Spinning the basketball is going to require friction. Spinning the baseball is going to require friction. Friction is going to be important to maintain the grip on the bat as you swing through. I mean, how many times you bat flies out? Friction forces so important. Running, jumping, throwing, activities of daily living. Like I said, you're going to be working with elderly people and children in gripping and grasping and doing and handling, and all of the things we do perpendicular to our grip requires friction forces. Okay, so being able to see these friction forces and how they play out in our lives is going to be important for us to know how to help people more optimally, because we understand all of the different things that are influencing their movements. Okay, if that makes sense. So to summarize today's lecture, resultant forces are broken up into X and Y, but the sense of those forces aren't exactly the same. You have direct compression components of pushes, and then you have micro components of that resultant micro pushes that are perpendicular to the direct compression. Let me see if I could do this. Yoink. Yoink. It's kind of like, and those microscopic interlocking pushes that are perpendicular to the direct compressions, we call that friction forces. Okay. So I hope you guys have a great, safe Mardi Gras break. When we get back to class on Friday, we're going to start into the meat and potatoes, movement strategies, and how we use these movement strategies for different skill. And then we'll start applying that to your projects and trying to bring all these different things we've been talking about into practice and application through your interest of your specific project area. Okay. All right, guys, y'all have a great day. And if you need anything, you let me know.